like they do at Akamai. Yep.
So I think I can see your screen, so I need to bring mine. This is a very odd position to look at the slide.
This thing is out of batteries. I should have asked her for batteries, darn it. Is the what?
Yeah. No, it should be on.
Does the laser work?
It works.
Oh. It's probably exactly. You want to share it?
That would be awesome. The qualification.
That would be
one button is.
Awesome.
I'm just like, I found like the button really impressive.
I put in a help ticket in the BOF this morning because I couldn't get it to go on. And they came in and they handed it back to me and they're like, all fixed. I'm like, now I know what they did. Yeah. Is it? Somebody said Zed.
Yeah.
Is Zayed? Zed? How do you say it?
Zahid.
Zayed. Okay, that's what I thought you said. But
yeah. Zero.
What?
Zero.
Zero?
I should rename myself to something like Mr. Jed.
I've got some friends who have Indian names. They go to Starbucks and they say, my name is Joe, just because otherwise it's more work, over and over again. Somebody you're never going to see again. It's not like you're going to get the benefit of it later on. 10-minute break is kind of short. Yeah, Guy from Ericsson was here talking about congestion control.
Yeah,
Ingemar, yeah.
Yeah, I mean, he works with me on this.
Oh, he does?
I don't get congestion control.
Oh, okay.
And he's more of a radio guy.
Yeah, somebody said, well, what's the performance like if you turn off the packet loss hiding, basically ARQ? And he's like, I know, I never thought about that before. Why would we ever do that? Try it sometimes.
Yeah, me and him on the same city, same building, same corridor, but he's working with wireless access. I'm working with media. So we both combine together and build this screen.
Ah, I see. I didn't know that you. Now I know just a little bit about Scream. I was preparing for my things tonight.
And then I then saw like, now let's see if I can plan what I'm going to say.
Good idea. Go ahead, think. Take a moment. Take 2 moments. You only have an hour.
I have to be so convincing, I guess.
I don't need that. Okay, we only have an hour, so we're going to get started. Only 5 minutes late. 4 minutes late? I think we're supposed to start at 18:30, right? Okay, so I've got 2 diligent minute takers. So anybody who would like to be the Jabber channel, all you have to do is watch the Jabber room, and if somebody asks a question to the room, channel it to the microphone. Anybody? Yep, clock's ticking. Is there anybody here with a laptop computer? Anybody? Laptop? Watch the channel, Jabber. Thank you, Colin. For Jabber channeling. Appreciate that. Colin.
You want to do that, Varun?
You do have a laptop, don't you, Colin? All right, excellent, excellent. Then you meet the qualifications.
You should hand it out.
Okay, I'm making friends today. Okay, so you are in the TAPS working group. Here's our agenda for today. We actually only have a 60-minute slot, so we're already 5 minutes late. We're going to move expeditiously. We have updates. Basically, the agenda sort of boils down to we have updates on a few of the drafts that are in progress. We're going to hear about a couple of related research and implementation projects, and then go get beer or whatever happens next. So the main piece of our first milestone, which we've been referring to as Doc 1, draft IETF TAPS transports. We finished working group last call. We gave it to Spencer. Spencer had some comments. Brian read the draft, and so I don't believe there's any outstanding comments. And so I believe the next step is that it's going to go to IESG review, and so that's the first half of that document. Then we agreed that we were going to add in. Oh, look, a little message about my Verizon coverage. We agreed that we were going to add in the TAPS transports usage as a second part of the first milestone. So it's not really a charter. It's not a charter change. It's just that the milestone now has got multiple documents in it, and so we're going to hear an update on that. And so one of the questions to talk about is whether that's done. Draft casing TAPS MinSet is a document we've talked about a couple of times, and so I think this is a first cut for our second milestone on identifying a minimum set of services that TAPS will support. And so another question we have is whether that's done. And so we're going to be hearing from those authors today. And then, like I said, there's a number of implementation and research efforts going on that are related to TAPS. And so I think that's actually very promising that there's some work going on, and maybe we're getting to the less arguing and more doing phase of the working group. Here's an update on the schedule. So these dates reflect changes that we agreed on at our last meeting. So we're going to try to finish the first milestone by the next IETF meeting. Hopefully that means finishing up the usage documents, and then by the subsequent IETF, finish up the MinSet documents. And I don't think we can really know enough about what's going to happen after that to know whether the November 2017 date is realistic or not. At this point, I hand it over to my co-chair, who has a few comments on scope.
Yes, thank you. Yes, we chairs have been thinking about these TAPS, where it's going and what's the future of it. And there are some topics that's popped up, and we also have been watching what's happening in the mailing list. And this is about a thing that personally I think have been missing, that we have not been discussed in TAPS, and we both agree like we should actually give you some hints about that. So basically, TAPS says you abstract everything from application, not everything, as much as possible. But actually, the applications, they're kind of getting smarter and smarter, and this is because also like they had to choose like what transport they use, and they had to like do some switching between the transport they use. So they actually would like to know what's going underneath. I mean, if I want to send a packet, maybe I'll change my behavior if it's using an TCP as a transport or EDP as a transport. This is happening, and this is kind of like self-tuning. You don't, if you know that, you kind of behave, you kind of package your information in a different way if the transport is different underneath. And another thing is like the application, they're responsible for the user experience. So if the application doesn't work, it's actually nobody's going to blame the transport. Listen, like this application doesn't work. So basically what's really important is like when it doesn't work, and how do you know like this like transport happening? And also there is a like robust predictable behavior we need from the applications, and that means like in some network, you may actually get this selection of transport pretty fast, and in some networks it might take time. But this application needs to know why it's happening. I have a session setup time. So it also matters, like time to get the first byte. This also matters. So that's also information, and then that kind of information maybe application would be like to have from going northbound, and some information like service cost. I mean, usually the server, if it is a client server environment, the server knows lots about the cost, operation cost, and stuff like that. So it might actually need to optimize, and it might also need to get this information back to the application, like whether they want to use some connection or not, or move between some connections, like a cellular via paid by versus non-paid path and stuff like that. And another observation we have made, like, okay, there is a mobility concern, and we used to think like mobility means like you're moving and you're changing your IP address, so you have like multiple. You have a new path that you actually would like to continue your session with. But it also, the current kind of trend is like, okay, when you change your path, you might also need to change the connection, the attachment point to the service provider, like, or the servers. So that's the new norms. And whether you want to, application would like to actually perhaps know this information and behave something differently. So these are the observations we made, and we think like this working group as a future-proof, and also like not only future-proof, like in current way, if somebody wants to use TAPS and make it and have these TAPS really have useful to them, the TAPS working group need to think about this kind of northbound information. It's not about what you hide or expose, what is hide, or I mean, the TAPS should actually make the application developers' life simple but also it should give some information back to the application so that they can do some kind of self-tuning, self-behaving, this kind of thing. So the northbound information is important also. So when you are doing work on the TAPS, I think this is one more thing that we need to think about. But that's it. I don't think we're going to discuss it in details because we don't have time, but it's for perhaps something to think about.
So I think the last missing bullet from the slide is that there's already a thread going on the list, and that this is related to that, exactly. And we should continue to discuss it.
Yes.
Nine? Let's see if I can just... I have a clicker for you.
You have to stay in the box.
You have to stand in the box, but here you can
Otherwise-
advance with this. Yeah. Don't blind anybody.
Okay, so I have to be closer. So this is an update on the draft IETF TAPS transport usage, and so basically we updated from 00 to 01, and one of the first things that we updated was we provided some clarification on how the nomenclature in the document was defined, or what actually that means. So basically, it's kind of set somehow in a static way that the categories can either be connection or data, and the subcategories for the connection you would have establishment, availability, maintenance, and termination. So that's basically kind of clarification, because some people got it wrong in a way that you could actually read the RFCs and could come up with kind of some sort of random categories. But here is like sets those categories in a clear format. Then the next thing that is added to the document is basically we incorporated the MPTCP into the 3-pass process, and we had a contribution from Christoph from Apple, and we incorporated 3 RFCs of MPTCP in the document. And using that, basically MPTCP provides some additional services that we have. Using TCP and SCTP, it provides on top of that some additional services on the pass 3, which is basically adding a subflow, removing it, or disabling MPTCP because it's already like in the kernel. So, and we also provided a change to the rules in the document that allows basically to use experimental RFCs in addition to the standard track RFCs, so that we could have the possibility of including the MPTCP RFCs. And then with regards to the discussion that we had in the previous IETF about the incorporation of DTLS into the document, we had some conversation with the TLS chairs. We also got in touch with the UTA chairs. And the feedback that we got from the TLS chairs was basically, we've got lots of documents that incorporate the TLS without actually describing an API. Also, we've got lots of features that are deployed in different applications that are also not described in the TLS spec. So in addition to that, the TLS has got lots of options that relies on X.509 and making it actually more complex if we would try to come up with some sort of definition of an API. And we would either end up having a too simplistic API or too complex, and that it wasn't really possible to come up with the right trade-off between having an appropriate API that is, rich enough and not so complex to actually do the work. So the conclusion, based on the conversation with the TLS chairs, as well as the talks with the TAPS chairs and ADs and the UTA chairs and on the mailing list, was that actually we don't think that we have the currently we don't think that we have the expertise or capacities within TAPS to actually write that section. So we're gonna leave it at that. And the future plan for the draft is basically to incorporate all the CTP related documents, RFCs that are beyond RFC 4960, basically to cover different CTP documents. Some of them basically have their own API related subsections. In addition to that, we would like to incorporate some experimental RFCs that are related to TCP, like TFO and others that we need to check. Also, we have got a contributor, Marie-Jose, that is working on incorporating the DCCP, and this is going to happen in the future. And I believe that's my update, so it's a very quick one.
Okay. Any questions? Okay, thank you, Naeem. You want to say? Okay,
I'll say
next.
I like the next idea. Oh, don't mention the word. Changes since draft 01 is we talked to lots of people in the IETF. It was fun. They told us lots about UDP. There's not a lot of documentation about UDP. We gathered what we could. It's all in there. Next slide. We did a bit of work. We actually tried to implement what we wrote. So there is some running code in the Neat project GitHub, which now supports UDP, which is a little bit of a triumph for UDP. UDP is not that difficult. Aha. Or so they say. Next slide.
We'll fix that.
Yeah, we're not going to carry that one on. I think we're done. We did what we set out to do. We wrote down everything we discovered about UDP. It's in the draft. We could get more feedback, but I don't think we will get a lot more useful feedback. I guess we've gathered all the low-hanging fruit we can find. The only question I've got is, it's now 20 pages long. It's got about 30 references in. Is it a stupid question to ask, do you want to publish the document in 2 volumes with the other working group document and get some UDP reviewers on the UDP stuff and TCP reviewers, SCTP, and other reviewers on the second document? Putting 2 together, I think, might be interesting to get IESG review and other people's review and IETF last call. I don't care. I've done the text. I give the text to the working group. If the chairs and AD decide they want to publish separately, I could see a rationale for doing that. Otherwise, I'll work with the main editor to produce 1 document. Question to the group.
Perhaps any IESG members that are in the room who are going to have to take these documents through IESG review would have an opinion on this. Or not.
Would you like 1 big document or 2 smaller documents, Spencer?
2 medium-sized documents.
All right. Well, okay, no. 1 medium-sized and quite small document compared to NFS.
A comment?
I am in favor of keeping things in bite size. So I hope for this.
Spencer Dawkins, responsible area director. I would always say do the right thing. I'm fine taking documents through in smaller pieces. I would be fine doing that. I would encourage you not to use NFSv4 as a standard, but which you decide how big a document can be. And I say that with love for the NFSv4 guys.
I think you just want to make sure that there's appropriate cross-references, so you don't end up reading one and not being aware of the other. I think that's the risk of having them separate.
I'm happy to work with, and there's going to be work done to coordinate with the other editors anyway, so I'm happy to take it either way. I don't need the working group to tell me no, but I say if we do publish it as a pair, they should be tracked as a pair. We should freeze them and let the working group do maintenance on them until they're all ready to be published.
It's a good idea.
Spencer Dawkins again. If they have cross references, they will tend to move together. If they have normative cross references, they will really tend to move together.
Is there any reason just to keep it as one? I mean, if you want it as one as well. So
So I voiced the only concern that I had. It's not a major concern, and I didn't hear any concerns in the room. So I would say, would you send a note to the list saying that this is what we plan to do, and for people to speak up so that you don't end up wasting your time going in the wrong direction. But I think this is probably what we should do.
Okay, you probably need to give it a working group name as well if you're going to. Because it isn't at the moment, it's an individual.
I've forgotten exactly how you do it, but we'll do that. Yes, we'll make that happen.
All right, I'm done.
Okay, thank you.
So just for the record, as one of the authors of the other document, we're fine with either decision. So
excellent.
Yeah, I'm going to make this quick. It's the MinSet. It's a pretty small update. Just for context, this is about the second charter item, charter part that reads that, well, the subset of the transport services coming from the first item will be defined here. Not all the capabilities need to be exposed. I will start with the caveat, with a statement about abstraction. You know, remember, abstraction is a trade-off. So TAPS is about identifying more services than we normally always use, identifying all the things from all the transports that at least we care about here. And if we expose all of that, we make all applications happy, but we haven't really achieved very much. If we also expose the choice of the transport, and then we haven't achieved anything. So we need to make it possible for this system to automatize some things. Doesn't mean that you need to always hide them, but describe the possibility of hiding things. And this draft is about these trade-offs. So this is the draft that hurts. We categorize things as being functional, as optimizing or automatable. This is nothing new. We have had that already, but we have simplified things a little bit. So functional would be things that you cannot realize without involving the application. There's just no way that you could automatize that or do something. Optimizing is something that, I mean, nothing is going to break if you do it, but you can't reasonably do it without the application. Like, you know, if you don't, for instance, yeah, change the SCP, or you could have Nagel, for instance. And automatable is the thing that sounds painful. So here I'm saying set primary path, for example. There may be situations where a TAP system can make a decision to set the primary path, for instance, in an SCTP, or make decisions about multipath or certain such decisions on its own without involving the application. No way you could do this with on-order delivery. So this kind of categorization is what we're looking at. Notable changes, not very many, but few things that are worth mentioning. So we have made two major decisions in this document. One is that, about making things, calling things automatable, saying it's possible to do things with them automatically without involving the application. That would be multi-streaming and multiple paths. I hope people hate this, so that we have some list discussion. Maybe not so much discussion here, so we have time for the other presentations as well. But voice your opinion. Get a bit active on the list, maybe. There was a category called deleted. I don't want to go into it because we just removed it. It turned out to be a redundant thing. There are now brief implementation hints everywhere. I believe that this group could need more activity, and the hope that we get more activity when we start discussing code and start discussing how to build such a thing. So this is where it begins. There are some hints about how we think these things could be implemented. Please take a look at them and tell us that you disagree and it couldn't be implemented in that way, or maybe some other way. So we have implementation hints. We have some small fixes that were applied to step 3 of the first document, but this is like halfway of updating to the newer version. I think that's it.
So in the interest of starting a small argument, just so that we're not wasting our time here looking at slides. Oh, sorry, Brian.
I wanted to start a small argument.
Oh, darn it. Well, you weren't fast enough.
Can I start a big argument?
Let me ask my question first, and if it turns out that mine doesn't start an argument, you can have your turn.
Not small and blow it up.
So when we say the API will expose multi-streaming and multiple paths as automatable functions, does that mean to say that it will prohibit the ability of an application to have the ability to control multi-streaming or multiple paths, or just that you're going to require that the application need not do that if the API is there?
I don't think the point of TAPS is to prohibit anything.
Okay, so
prohibit.
applications that want to get their fingers into that kind of control will still be able to do that, and we're not going to prohibit, but we're going to say, oh, we as a working group are going to make the effort to expose an API so that apps don't have to if they don't want to.
Yeah.
Okay, well, then I don't have any argument. Your turn.
I'm trying really hard to have an argument, but that was my non-argument, so thank you.
I think you can sit down. No argument here. Oh, so wait a second. So is the document, are you saying the document's done?
Absolutely not. I'm sorry. Very much not.
So where's the part where you say the stuff that needs to happen?
All the stuff that happens with the first document. So this is based on the first. So the first is going to grow. There's a lot of SCTP RFCs that are not covered in the first. TCCP isn't covered in the first. All that.
Okay.
All that stuff needs to be incorporated in ours, because ours is taking that and going through the list and saying, categorizing these.
And do you have people who you think are willing to do that?
I do. I will do a lot myself. I promise.
So that's a yes.
We have.
That's good.
Yeah. Also for the second document. So this is just me and Stein, but this is less work.
It's mechanical.
Yeah. So this is going to be less work for the. I mean, I don't worry much about updating this when we get the first one to update.
Okay. So my comment is like the thing that you described to Aaron and Aaron described to you, it would be good to put it in the document so that we understand what exactly this automatable means.
Yeah.
In a clear way. Yeah. Thank you.
Sorry, we couldn't argue more. Joe wasn't able to be here. Okay. Anna? There you go. Thank you.
Okay, hello everyone. So I'm Anna Brunström, and this is a joint work that I'm going to present with a number of my colleagues in the NEAT project, and in particular, Georgios, the first name on the list there from Simula, is the one that did the majority of the work. So I'm just going to give you a summary of some of the ongoing research on happy eyeballs that we are doing, and in particular to look at the cost of the mechanism. So this is related to the third work item that hopefully people are excited to get to. So we have in the charter that we need to explain how to select and engage an appropriate protocol and how to discover which protocols are available for the selected service between a given pair of endpoints. And of course, if you're going to do this and you don't have some a priori knowledge or explicit signaling, the way to find this out, if a protocol is supported, is by trying it out. So this calls for some kind of happy eyeballs mechanism to solve this problem. And happy eyeballs, of course, is when we don't try different alternatives serially, because this will take a lot of time and delay for the application. So instead, we look at trying multiple transport solutions in parallel. So we have done some measurements, because if you're now going to test a number of protocols in parallel, this is going to be nice for the delay, but it's also going to come with some cost, right? So the the aim of this first work has been to look at this cost, and in particular, what is the cost on the server side? Because you're now going to have to deal with multiple connection attempts in parallel. So this will require some extra processing and some extra memory at the server, potentially. So we've had set up some experiments where we have a web server supporting both TCP and SCTP, and then a custom web client sending parallel requests using a happy eyeball mechanism. And then in the middle, just an emulator to add some delays to the experiments. And we looked at 3 different test cases. So the first one, very basic, the simplest scenario, where you just have a connection that starts and there is no encryption, there is no caching. So in a sense, this is the worst case scenario for happy eyeballs, because every connection request results in 2 connections going in parallel in this scenario where we look at 2 protocols. And you also don't have a lot of other processing going on which you can amortize this cost. And in our experiments, we looked at sending these happy eyeballs requests at varying request rates. And we also looked at downloading 2 different sizes from this web service, so a 1K page and a 35K page. And I'm just going to show you here some results for the CPU utilization. For memory, we didn't really see any major impact at all, but there is a paper on it with the full results. So this is kind of a teaser to get you interested, and then you can read the full paper. Okay, so this is the first basic test scenario that I mentioned, where we have no encryption, we have no caching, so we're just sending 2 requests in parallel. And what we have on the x-axis is these different loads that I talked about, so sending at 100 requests per second or 1,000 requests per second. And each experimental run here lasts for 10 minutes, and then of course we had a number of these. And then you see the CPU utilization on your y-axis. The 2 colors is the 2 different object sizes. So the blue one is the 1K byte, and the red one is the 35K byte. And the easiest is perhaps to look over here at the 1,000 requests per second, because then we have the largest bars. And we can see that if we just use the graphs here, TCP means no happy eyeballs, 1 TCP connection. SCTP means no happy eyeballs, 1 SCTP connection. And then we compare this to happy eyeballs and with an outcome of TCP being selected. So we can see that if we just run TCP, and then if we run happy eyeballs, we're going to increase the CPU utilization. It almost doubles here. And that's not surprising, right? Because we're sending 2 requests and there's not much work. We can see that already if we increase the size of the page, this difference is going to be smaller. And we can also see that using SCTP in this case, the 2 protocols differ. So you actually have not much of a difference when you go to the larger page size between getting an SCTP, just using an SCTP service, or the happy eyeballs when the outcome was TCP. So we're seeing that already here, the happy eyeballs is actually not perhaps such a dominating cost. So this was the first test scenario. The second test scenario is the same setup, but now we add TLS into the picture. So the connection now uses TLS. And then we can see that, well, maybe I go back and I show you here that the CPU utilization was about 6% here. If we add TLS, you see that the CPU utilization goes up to 25%. So you can see that the impact of TLS here is much larger than the impact of happy eyeballs. And of course, that also means that we now have a much smaller difference between the protocols here. Even when you look at the 1K page size, it's not a big difference between the different mechanisms. And this is, of course, quite expected, right? Because when we now are doing much more work, the cost of doing the extra happy eyeballs is, of course, getting smaller. So then in the third scenario, we add caching into the picture. So if you want to implement this, of course, you wouldn't like to every time try everything, right? You want to learn when you're doing something. So if you know that the protocol succeeds or that the protocol does not succeed, you don't need to try it. So if your preferred protocol proceeds, you can try that immediately and maybe not try the other candidates, or if there's something you know doesn't work, you shouldn't try that every time. So we have now added caching into all the scenarios you saw before. So here we have the unencrypted scenario, here we have the TLS encrypted scenario, the 1K page size, and the 35K page size. And now we don't have the load on the x-axis anymore, now we have the cache hit rate. So over here we have a cache hit rate of 0, so that means the case where we try happy eyeballs on everything. And over in this end we have a cache hit rate of 1, which means that you never have to do happy eyeballs. In this case the outcome was always a TCP. And then here a range between them. So this is 0.8, it's very hard to see in the slide, but 0.6, 0.4, 0.2. And perhaps if we look at this scenario, because this was the case where you see it's easiest to see. Of course, if you add the caching, this is going to help you, because now you're not going to have to do the happy eyeballs mechanism all the time. So if we look over here at the 80% cache hit ratio, you can see that the difference between using happy eyeballs or not is not really big. And of course, if we go to the TLS encrypted case, here it's already a smaller difference between the protocol. You see some impact of the caching, but it's already quite similar. And if you're wondering at the different 3 bars here, that is the outcome of the happy eyeballs mechanism. So in the previous graphs, it was always TCP that won. Here we also have added, so TCP being the winner, SCT 50% of the time. So either of the protocols can win, or always SCTP being the winner. So this is just showing that you have some difference also in the overhead depending on, or in the CPU load depending on which protocol you are using. Okay, so this was a very quick summary of some of the results from these measurements. And I think the conclusions from the results that we see so far is that it's feasible to use happy eyeballs as a transport protocol selection mechanism, because you're going to amortize over the cost of all the work for the connection, and with caching you can also reduce the load quite a bit. So the experiments here was done, you know, as a separate component, as I showed you, with a standalone just a custom web client and the server. So we're also now building this happy eyeballs mechanism into the NEAT system that was mentioned also on the previous slide here, that we're building in this NEAT project, which is a TAPS-like system, and the code is also available here. So with that, of course, we want to do more extensive evaluations, also measured in real networks. And we also submitted first very rough draft of the happy eyeballs framework. So this is something that we will update and continue working on. But we're of course happy for feedback, but we will also come back with a bit more polished versions, and that you know on the list when those are becoming available. Questions?
Hi, Tommy Pauly, Apple. So how parallel are these? Are these completely parallel, exactly the same time attempts between both? Yeah, okay.
Yeah.
So just coming from our experience with V4, V6 classic happy eyeballs, and having done our implementation, we found, you know, like a staggered race kind of mitigates a lot of the factors of overhead and CPU. So is there a way that so in those cases, we can guess from like previous RTT which one we think is faster, and just try that one, wait until we think it should have finished, and then kick off the next, and that has a very high success rate for us. Is there something we could do similar for protocols here, of guess historically which one we think is better and race them a little bit staggered?
So what we're actually suggesting in the draft and in the framework for it is that you have some notion of which protocol will provide you with the best service, whether this comes from knowledge of what the application needs or some policy system, or so you actually try the preferred transport a little bit before the next transport. So kind of having a priority for what you would like, you know, the outcome to be, so that you have some, if the best protocol doesn't work, you have a fallback that you have initiated with a small time delay, so you don't have to wait for the entire connection and the very long delay you can get if you have to wait for it to completely fail.
It would be great if, in addition to kind of like the a priori preference, you could also have some type of learning mechanism.
Of course, so that you then have to combine with the caching, right? So if you have protocols that didn't succeed and you have recently tried them, then I think you should not try those at all. And then eventually you have to time out that so that you probe it at regular intervals, but clearly you should not. And similarly, if you have your preferred protocol was just successful, then maybe it's enough to just try that, right, to start with, because you have or at least the delay should be much larger before you start to open another connection attempt. So definitely, this is something that we plan to have in the framework. So the way that we are thinking about it at the moment is to have some kind of priority between these solutions that we combine with the caching information. Does that sound like a good approach, or do you have suggestions for other ways to manage this timing?
Steven Strauss, I'm not going to answer the question. I just want to make some trouble.
Okay, that's fine too.
I mean, I like this idea of running a happy eyeballs type thing for transport selection. How does happy eyeballs operating in the transport layer interplay with happy eyeballs operating in the network layer, and how do you race different things happening at the same time?
Yeah, so I think that you need to combine these, right, in some way. So
right, and I mean, I was talking to folks about this earlier, but the way that lots of real-time applications do this is with ICE, which is for connectivity establishment and gets you into a really messy place and a really nasty algorithm with lots of preferences specified. I wonder if it gets as messy as that, or if there's a neater thing that can come out of TAPS.
I think it depends on which protocols you have to select between, right? But that is a messy case, and that we have not worked that out. So this was the reason we started with TCP and SCTP there.
Tommy Polyapple again. Just in regards to that, we have a bit of experience with double happy eyeballs between, not transports, but between address families and then interfaces, so that we'll have double levels of that. And if you do it carefully, it can be okay. So yeah, I think it'd be good to specify something like, if you are doing that beneath, just make sure they're kind of independent layers, and have to.
But we're saying that there's going to be yet another. This is additive, right?
No, I know exactly. So this is like a third layer, so you could have giant trees. But ideally, your TCP attempts and your SCTP attempts or whatever, if they need to have their own happy eyeballs for V4, V6, that's completely up to them, right? It's kind of abstracted at that layer.
Oh, good. We're getting a discussion going, but now I'm worrying about time. So, so please try to be brief.
Varun Singh. I'll just, so ICE met today, the working group which does interactivity, connectivity establishment, and they had really good results and actually a lot of ongoing discussion around that. So I think Colin Jennings ran an experiment where he bought a bunch of NATs and he ran a test, and he said that he could basically paste the checks at 5 millisecond intervals, and they all went through. But what they found out was that there are about 36 candidates pairs for each address family. So there were 72 total checks that needed to be done just for IPv4, IPv6, and they have like relayed candidates and so on and so forth. And they found out that if you did this, there would be 1 megabit per second just connectivity traffic, like right at the beginning of there's nothing even started. You just press call and this starts up, right? So the group went through a lot of discussion, and of course there's UDP and it's not congestion controlled. So basically the only thing that's controlling the whole checks is the timer, like TA, that's the timer in 5245. So like coming back to here, at least it's a tractable problem in the sense that there are some transports here which are like TCP and SCTP, which are congestion controlled. So when you send out these things, I'm hoping that they are like following the congestion control behavior. But again, you have IW10, and you could actually send out a lot of packets. So
this is in the connection setup. So unless you have fast open, you're not going to have data in the SYN. But
yeah, it depends on what the connectivity. In the case of ICE, there is a stun packet, and the stun packet has a lot of data.
Yeah, I was talking about TCP and SCTP case.
So I think the question, again, if you have 72 candidates here to address families, and then you had UDP and TCP and SCTP, you can just do the math to figure out like 72 times 3 in this case, and that's a lot of stuff to go through. And I think what we're looking for is, if you come up with a guidance here, then ICE could basically like take that guidance from here into their working group. So I think this is a relevant discussion to have. And actually how you do the connectivity checks for whatever case may be, it is guidance to other groups.
Hi, Colin Perkins. Yeah, I came up here to say something like how Varun just finished. This is essentially ICE. The bits are encoded in a different way, but you're essentially running the same sort of algorithm. There's clearly scope for some cooperation.
I agree.
Michael, you?
Michael Tuxen, just wanted to note that at least in the NEAT project, what we do is we control the protocol selection at the transport and network layer completely. So we don't just let the operating system choose. We choose explicitly, we want to test this over v4, we want to test this over v6, and try to avoid these two layers of interaction which we can't control. So that's the way we're approaching this there. Control the stuff. I mean, we are aware of this, and we control it and try to do something.
Thank you, Anna.
Okay, thank you.
Brian, it's your turn.
All right, it's only now. Sorry, somebody said I next group just left together. So, hi, I'm Brian Trammell. I'm going to give a very quick talk about something that I mentioned at the microphone at the last meeting called post sockets. The idea is that really a lot of the work that we're trying to do here to make everything more flexible is kind of running into the fact that we're using yesterday's interface, stock stream, right? Like I said at the plenary last night, for the people who didn't have better dinner plans, we have a really great interface for getting a tape from one side of the room to the other, and an excellent protocol for getting a tape from one side of the room to the other. But you're running into problems with scaling the protocol, and we're also running into problems with scaling the interface. It's synchronous, it's unicast, it's got no framing support, single stream, single path, there's no path abstraction, there's no security, and you can measure it, but everything is implicit, right? It does make the network look like a file. I don't want to say that this was a bad idea. This is the reason that everybody who could program a Unix machine in the 1970s became everybody who could program internet programs in the 1980s, which is the reason we have an internet. It's also a reason that we have an internet security problem. Fortunately, about 15 years ago, some very smart people, many of whom are in this room, came up with sock stream, which is yesterday's interface today, right? We can actually get this. It's still synchronous. Nobody really cares about unicast though. Is multicast routing and security are too hard. I mean, it's like you just say multicast 3 times and Aaron is like, he declares the BOF over. There's no framing support, but nobody cares because the lack of framing support in TCP means anything that runs over TCP that needs framing support invented it anyway. Single stream, you know what? Actually, we can just open multiple flows. We figured this out as soon as we started inventing browsers. MPTCP looks like it's actually deploying, so that fixes the single path problem, and TLS and OpenSSL solve all of our problems, so we don't have to worry about security, right? We're still missing a path abstraction, and the question is, can we do better than this? So if you look at seek packet, it actually sort of fixes most of these problems. You get unicast or multicast, you get framing support, single or multiple stream. You get multipath for failover, but you can actually control it, so you can also do it for bandwidth sharing. Still no security, still no path abstraction. It is bound to the SCTP, which is not super deployable in the open internet today unless you run it over something like the thing that we were trying to invent this morning, but won't be able to for a few more IETF cycles. So these are insights that I had while staring at this problem, which might also just be silly assumptions. Silly assumption number one is that applications deal in objects of arbitrary size. There are a few times when you actually do have to stream something from one side of, like when you actually have the problem that you have a tape and you're trying to get to the other side of the room, you don't know how much more tape you have, right? So sometimes you're actually streaming things. Often you're not. Often you know how big the objects are, or can come up with a stream of objects that are of the same size. This is how we've done video over TCP, by the way. We keep saying multipath. People jumped up in Plus this morning and said multipath, 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 and we said yes, yes, yes. I think the network of the future is explicitly multipath. It's not going to be that often that users or servers have only one route out to the network. I've heard of crazy people already running BGP all the way to the top of the rack switches. I think that basically saying, and this was one of the things that we talked about when we were putting together the TAPS transports document, saying that security is not really a property of transport, that is a property of some upper layer. I don't really think we can get away with that now. I think future transports have to guarantee these properties. The fourth thing, which is harder to do on the API side, is that message reception is inherently asynchronous, right? Somebody's going to send you a packet or a stream of packets, and the transport layer is going to put them together and then goes, hey, you have something. And you know, sitting there and busy polling or busy waiting on it, or running a thread for everything, you know, like, you know, anybody who, I think there are a few people in the room who are of the age where they learned programming with Java before NIO. So, I mean, like that, if you actually look at how things are coming off the network, everything is inherently asynchronous. And if you look at how scalable programming works right now, it's enabling this asynchronous programming, and some of them even actually require you to handle it asynchronously. I'm going to shorten my talk, so I'm not going to go through this slide. This is basically, this talk is an advertisement to read this slide. This is my, it's obvious if you stare at it for a couple of seconds. There are some boxes, and we also have some lines.
Nice.
The idea here is there's an association. The association has some, you can send some objects to the association, and then there are some events that come off of things, and you can bind handlers and stuff. And this is intended to start a discussion about if we were going to throw it all out and start over, knowing now what we wish we had known then, with the programming models that we have now and the hardware that we have now and the operating systems that we have now, what would it look like? It would have very nice rounded lines and be notated in Gill sans. Yeah, I'm not going to go through these either. Why am I talking about this in TAPS? TAPS allows you to select transport protocols, but if each of those transport protocols inherently needs its own API to deal with, right? So if you're writing to SOC stream or SOC seek packet and you get TCP, there's got to be a shim layer that makes TCP look like SOC seek packet in the end. So if you're trying to do this, you need an API, a single API that runs over all of these transport protocols, no matter what their properties are. The need API is one solution to this problem. It looks a lot like current APIs. That's actually a pretty good way to go about it if you want to minimally disrupt existing application programming. But if you're going to have to touch the application anyway, why not go with this more radical approach? Anyone who's interested in talking about this, unfortunately, I haven't had time to work on this since the last time I mentioned it at the mic. Please, this is a, I wish I had a paper published to point at this. Actually, Colin published most of the paper because this is like 3/4 of the TCP Hollywood thing. Is that what you were going to say? Yep. Yeah. Read Colin's paper about my awesome API. I guess we have like 3 seconds for questions, or because I want Stephen to get up and have a chance.
Let's have a couple of quick questions.
Okay.
Colin Perkins, yeah, I was going to say what he said I was about to say. If you add deadlines, you've got something that looks very like the presentation that Stephen will be doing later.
Yep, excellent.
I also wanted to say Clark and Tenenhouse application level framing.
We call deadlines lifetimes. Sorry, again?
Clark and Tenenhouse application level framing, SIGCOMM 1980 mumble.
Yeah.
Oh, okay. I got to go read some stuff. Thank you.
I mean,
can you send me that? Can you send me at least the Clark and who? Oh, that one. Yeah. Okay. Yep.
Architectural considerations, new generation protocols.
Yep.
Tommy Polly, Apple. I think this is great. I like your model. I think it's very similar to a lot of what we're doing. I think the tricky thing will be getting everyone to agree on it and actually having something that people use. So I think it'd be important to early on get a discussion group going of people who are actually implementing the stacks that people are using for networking. I've had some conversations this week with people about doing that, and so we should loop this group in with that group.
Yep. Sounds excellent.
Awesome.
Thank you.
Okay, thank you,
All right,
Brian.
thanks a lot.
I forgot to mention at the beginning that because I had sent email to the list that we're going to run probably about 10 minutes over, that we had a last minute talk that came up at the Applied Networking Research Workshop on Saturday. And so we're squeezing it in, except, is Philip here? Oh, good. So just FYI, Bits and Bytes doesn't start for 20 minutes. Wait, I think we have one more. Oh, yeah. What's the last one?
The last one is...
Oh, Stephen. Oh, that's the last one. Right. So it's not Philip, it's Stephen who's the last one. Okay. No pressure, Philip.
No pressure for a 5-minute talk. Okay, fine. So today I want to talk about socket intents. This is our try to automate something, namely the access selection problem, on yesterday's API. And trying to do this, you really need some information. And one of the most valuable information you could have for access selection is the question, what's the application going to do with this socket it's now opening? And thinking about this, the obvious answer is applications know more than they can express using today's socket API, namely nothing. So if I have something like a web browser, it's most probably knowing what's approximately which size of an object it's fetching, or if you have video streaming, it's knowing it could tell to the socket API. I'm trying to download something that will have a constant flow, or more or less constant bursty flow of information, and not something that will just fetch 20 bytes. So how could this look like? This is joint work with Teresa, where we've thought about how could this look like, and so that basic idea is, so the application specifies something in a very rough manner, saying, I will know this is something like a streaming data, or this is something like a bulk download, or just some control or chat flow. Something like, I know the file I'm going to download has 10 megabytes. Whether I care that the datagrams will be delivered timely, or whether delay is more or less no matter for me. Which bit rate or duration a stream might have, and how resilient the transport should be. So do I really care about packet loss, or is packet loss something, yeah, I will care about by doing retransmission, because the operating system update, nobody sees whether it will arrive 10 minutes later or not. Yeah, this got us to a table of some ideas how these categories could look like. Skip about that. And implementing this, the question is how to do this. We start with the original BSD socket API. We're thinking, okay, the best place to implement this is as a socket option. This is the least invasive way to do this. And first got on and modified all basic socket calls to include a context where we could bind the calls together, because these calls are really just loosely coupled. Later on, when trying to solve the problem on how to do this asynchronously, we found out would have been sufficient to change get other info in a way that we could provide all this information and afterwards return the information like the socket abstract, the socket should set, and the bind address the application should bind, so for doing the access selection. The next question we asked ourselves is, okay, if we want to put this for a web browser, we need connection reuse. And doing this connection reuse, also said we want to automate this. And I think this is also some point to take into account. If we need to do connection reuse, we need something like a more different API. We need something to first do some kind of, yes, we want to connect to a host and have just a socket call that gets everything the usual socket calls get at one place. And you see this wrapper in mostly all applications that are using sockets. And you need something that can do connection reuse. So you say, okay, I want to connect to the following host port. I have the following properties of the connection, and please give me a socket that I can reuse, or give me a new one if there is no suitable socket already open. And by having these calls, we can really speed up HTTP a little bit and take the burden from implementing the whole access selection, the whole connection reuse stuff from the application to some kind of socket API or shim layer that also does this automatically, which is really nice. And after the socket release, that reuse the socket or close it, I don't mind. Yeah, there's some so if you want to play around with it a little bit, there's a prototype on GitHub including the socket reuse stuff, and we released the most recent version 0.5 yesterday. So if you want to play around, have fun.
Okay, thank you. Just on time. We can take a quick question if anybody's got one. Okay, if anybody is determined to leave now, go ahead so that we don't interrupt Stephen in his talk. Yeah, thanks, guys, my colleagues. Thanks. Here you go, Stephen. Remember, you're between this room and free beer. No pressure.
Okay, so I'm Stephen McQuiston, and I'll be talking about transport services for real-time applications. So the approach of the working group so far for defining transport services has been somewhat bottom-up. So we've been looking at transport protocols that have been standardized, and we've been breaking them down into transport services that these protocols provide. Now, the approach that we take in this work is a top-down approach. So we look at the application, and then we work down towards the transport layer and determine what transport services the application needs. And we do that specifically for real-time multimedia applications. So we're asking what services do real-time multimedia applications need, and then we're taking that and we're following it down to the transport layer and determining how we can provide those transport services with the existing transport protocols. So just a quick note about these applications. They're characterized by a maximum delay bound. And for interactive applications, that's in the low hundreds of milliseconds. So for VoIP, for example, it's a couple of hundred milliseconds. That's based on human perception. So a delay above 200 milliseconds, and the interactivity breaks down and users start to notice. For non-interactive applications, the delay bound is in the tens of seconds, and that's based on the desired experience that we want to provide users. And ultimately, the services that we specify for these applications need to respect this maximum delay bound and this timeliness constraint, and at the same time add as little latency as they can so that we've got more of the delay to use up at the other layers of the stack. So that's the applications, and so we'll define a set of transport services that these applications need. And the first of these is a timing and deadlines service. So again, data has a set time by which it needs to have arrived to be useful to the application. So an IPTV application, for example, has frames of video, and each frame has got a time by which it needs to have arrived to be used. And once we've passed that time, once the frame arrives, it'll not be used by the receiving application. If the transport layer doesn't know about this deadline, then we run the risk of sending data that's effectively useless. So what we want to do is estimate the likelihood that this data will arrive on time. So we need the deadline for this, the data, an estimate of the one-way network delay, and some notion of how much buffering will be carried out at the receiver. And then we can estimate whether or not the data will arrive on time, and then make transport decisions based on that. This is really the fundamental service for this class of applications, and all the other services that we define will follow on from this one. And so the next service is partial reliability. So we know that IP gives us a best effort packet delivery service. So some packets will be lost. And we know about this timeliness constraint where data has a deadline after which it will effectively become useless. If we want to provide guaranteed reliability, then we're going to start missing deadlines, and we're going to start transmitting data that's effectively useless. So what we want is partial reliability. We want to retransmit lost data, but only when it's going to be useful to the receiving application. So only while the data will arrive within its deadline. Now, of course, partial reliability means that ultimately some data won't arrive. Some packets won't be delivered to the receiver. And so what we need to do is maximize the utility of the packets that do arrive. And this implies some sort of application level framing and the application sending ADUs, and so a message-oriented transport service. And given that these messages will be independently useful and we want to reduce latency, these messages can be delivered in any order, the order in which they arrive at the receiver, rather than introducing some sort of order. We then introduce a substreams service. So these applications are often comprised of 2 or more subflows, so an audio flow and a video flow. And we want to multiplex those across a single transport connection. So we have a substream service to do that. So partial reliability means that some messages won't arrive successfully. But if we look at applications, there's often interdependencies amongst the data. So an MPEG-1 application, for example, has IP and B frames and interdependencies between those. So if we've got an I frame with a P frame that's dependent on it, and the I frame isn't delivered successfully, then we shouldn't send the P frame either, because it's dependent on data that wouldn't have arrived. Of course, utility is quite difficult to define for these applications, because the I frame might not be useful in the sense that it won't be played out, but it's useful in the sense that the P frame that depends on it needs it to be decoded. So we have these multiple versions of utility. The next service is congestion control. It's important for protecting the network and other applications. We don't specify a congestion control algorithm for the application to use. We just simply say that one must be used, and that the application should be able to select an appropriate algorithm for use. And finally, we've got a connections-oriented service and a keep alive service, and that's useful in some scenarios for explicitly setting up and tearing down in network state. And so we've got this set of transport services for real-time applications. So we've got deadlines, partial reliability, message-oriented, substreams, dependencies, congestion control, and then finally connection-oriented and keep alive are the 2 optional ones as well. And so we need some way of providing these services at the transport layer. So if we provided them in UDP, we can see that UDP already supports a message-oriented service, so there's no change needed for that. Supporting partial reliability means that we need to be able to detect loss and retransmit messages if they're going to arrive within their deadline. We might need to add some headers and other mechanisms for that, and we'll need to add an estimate of the one-way network delay for that to function as well. Adding substream support means that we need to have a small header in each message, and connections and congestion control can all be added within UDP's payload. If you look at something like Quick, we can see how we might provide some of these services over UDP. More interestingly, though, we look at how we can provide them over TCP. TCP gives us a byte stream abstraction. So providing a message-oriented abstraction on top of that, it's not sufficient to put the data for each message in a single segment, because segments might be resegmented in the network, and so we need some sort of framing mechanism on top of that. And if we look at Minion and unordered TCP, we see a byte stuffing algorithm and a framing mechanism that would support that. Again, substream support means adding a small header to each message. TCP is already connection orientated and it already supports congestion control. Its congestion control algorithm is fixed, but we could modify the API to allow applications to specify the congestion control algorithm they want. And ultimately, that leaves us with one final service, partial reliability. So middle boxes in the network have ossified around TCP's reliability mechanism, and they do not expect to see gaps in TCP's sequence space. So that means that providing partial reliability isn't as easy as simply not sending TCP retransmissions. So we always need to send TCP retransmissions to ensure that the TCP sequence space is filled. But what we don't do is always send TCP's, the payload that would be associated with that segment. So if the payload for that TCP retransmission won't arrive by its deadline, then we'll swap it for another message that will arrive by its deadline. And this is a mechanism called inconsistent retransmissions. And we've done some small-scale evaluations with our prototype, TCP Hollywood, and some other people have done evaluations of inconsistent retransmissions, and largely it seems to work There are some cases where we see caching in the network and we get the original instead of the new version, but broadly it's safe failure modes for this mechanism. And so in summary then, we've defined a set of transport services for real-time multimedia applications, and we've shown that these services can be provided over both UDP and TCP. Ultimately, that allows us to use UDP in the majority of cases, but fall back to TCP and provide the same services as well. So this was part of a paper that was published at the Applied Networking Research Workshop last weekend. So I'd encourage you to go to the workshop website and you'll get the full paper and the slides for the full talk as well. And that is me.
Thank you.
Michael Tuxen, a lot of the stuff you can get with SCTP using PRSCTP and
yeah,
and
it's a similar API to PRSCTP.
Yeah.
Yeah.
Thanks, Stephen. This is really awesome stuff. It sounds like you actually have been drafted to get into the group of people on the stack side and also on the application side to talk about how to make this better. I'm a little skeptical of the mechanism that you're using to support partial reliability. I'd really like to see a larger scale measurement of that.
Yeah.
I know that you know this, but I want to say it in the room. Please consider if you have the ability to run something bigger, go ahead and do it and submit it to MapRG. If you don't, send mail to the maprg@ietf.org list and ask for help, because this seems like a really interesting problem to dig into. So again, thanks a lot.
Yep, thanks.
Thank you, Stephen. All right, well, thanks everybody for staying late. And I hope that in Korea we hear about more work on the implementation and the mechanism side, and as well as the MinSet doc. And thanks off. And we'll try to get a longer slot too. Thanks everybody for coming.
Yeah, thank you. Goodbye.
All right.